Okay, so guess what? After the sample chamber, we have a monochromator. But this is going to be easy for you because you've already seen a monochromator. This is the same type of monochromator that is used in a UV vis instrument. There's no difference in them because this is still a spectrometer at the heart. It's just a different light source. So the monochromator acts just as before. And if you missed out on it on the first time, I'm going to quickly review it again for your privilege. And the monochromator is basically a box. And inside of the box, light goes in and light goes out. So we're going to put in and we're going to put out. Now the light goes in, and that light could be made up of all wavelengths, or wave numbers in this case. Same kind of thing though. And traditionally it hits a series of mirrors. Excuse me. And the light goes and hits one mirror. Eventually it will hit that last mirror and come out. And then in between, we have a piece called, do you know what that thing's called? With the saw teeth, or what we would really call a prism, that is called a grating. So a grating is located on the inside, and the light will hit the grating, and when it does, that prism will divide it up into the red, if this was UV and vis, orange, yellow, green, blue, and violet. And then it would hit this mirror, and then that particular light would come out. So the monochromator, mono means one, chooses one, and chroma looks at color. However, it's not just color that we're using. In this example it is, but infrared has no color. There's no red, orange, yellow, green, blue, indigo, violet in infrared. So we really have to say wavelength. So it chooses one wavelength to analyze and report at a time. In the case of infrared, we're looking at 4,000 to 600 per centimeters. Notice that this is wave number. Wave number and wavelength are related. It's just a different unit that we use in infrared. So the grating separates the wave numbers from each other in infrared spectrometer. The grating separates the wavelengths from each other in a UV vis spectrometer. How are these two things related? Remember, wavelength is in units of nanometer. Wave number is in units of per centimeter. So if I have a nanometer, I can convert that to a centimeter through conversion units. And then I take 1 over that number and I get a wave number. All right, so that's the monochromator. There's nothing special about it. It's the same monochromator as before, and it still does the same job. We also talked about the teeth, or this prism on the grating. And the more teeth that it has, or the more saw blades, if you want to think of it that way, the better the resolution of the instrument. It can separate the wave numbers from each other in more detail. If I have a cheap, nasty grating that I've paid a little bit of nothing for, then I might be lucky if it separates whole numbers. 4,000, 3,999, 3,998. But if I have a really expensive grating, then I can go into 1 decimals or 2 decimals or 3 decimals and do a separation that way. So that's the story with the monochromator. It's the same as before. And then after the monochromator, we go into a detector. And the detector sees all of this information. And it looks at how much light is coming through with nothing in it, and how much light is coming through with a sample located there. The detector is the same as it is really in UV vis. Most of the time, this is a PMT detector, photo multiplier tube. And it works just as it did in UV. The light hits maybe a strand of electrons. It knocks that electron off. That electron goes through and it hits another plate and it knocks more electrons off. And then maybe 3 get knocked off, and then those get knocked off, and it multiplies the signal large enough for the computer to pick it up. All right? So that's the monochromator that comes after the sample chamber. After the monochromator, it goes into the detector to get picked up, and the detector relays that signal to the computer or software system so that way we can get a nice, pretty infrared that shows up on a computer screen. And that's all there is to it, people. So once you learn it one time, you typically know all spectrometers. It's just a couple of ways that they're different. And one of the ways for infrared is the light source. Everything else is very similar to a UV vis instrument. Now, since we're talking about the computer, I now want to talk about a library, because this is the first time, maybe, that you have used an instrument with a library built into the software. Because infrared is traditionally running pure compounds, not all the time, but a lot of times we know what that infrared should look like. And that's not going to change very often, right? That's pretty standard. If I run benzene, benzene is going to look the same every single time I run benzene. So over the years, companies have basically built a database. And that database is full of infrared spectra that I can utilize to my advantage. Well, our Shimatsu system has this database. And I can utilize that database to make my job much easier and makes me a happier person in doing so. So I can analyze a sample on the infrared, and my sample will go through the machine and I get an infrared spectra. And the software on my Shimatsu system, the software will take this infrared spectrum and it crosses it into a database with thousands of compounds. And my software will then give me a list. 1, 2, 3, 4. And it will be names down here at the very bottom. And it will say, based on our fingerprint search using this infrared spectrum, we believe that the compound is probably one of these. And it will list some names down here at the bottom of the report. There will also be a score over here to the side, and that score is a number. The higher the score, the more confident that the software is about identifying that particular compound. Really low numbers, it's not so sure about. It thinks it could be, but it's not going to put money on it. Really high numbers, though, well, those high numbers, it feels good about. We go to Vegas, we put our money on the table and put our money where our mouth is. I believe that the score in the infrared system is 1,000. 1,000 is perfect. So the closer it is to that number, the better it feels about cross-referencing that compound and identifying what that compound is supposed to be. So this is a database. The database comes from NIST, National Institute of Standards and Technology. So the NIST database is the database that we have on our campus that we cross-reference our samples with. A laboratory might have a different type of database. There's plenty of them that are out there, and there's numerous ones that are out there. But that really depends on the company and who purchases the machine. There are also databases that are just specifically for the ATR attachment. ATR runs things slightly different, not major, but some people want to feel comfort knowing that there is an ATR database that's specifically designated to that particular attachment. And they're there, and we do have some of those. But when we cross-reference with all of the databases that we have, not just one. Now, another database that you have access to is not a database connected to a computer software. But if you go and you Google SDBS, that stands for Spectral Database System. The Spectral Database System is a grant-funded activity that a group in Japan has assembled for you. And you can use this as you want. So here it is. This is why I always Google it, because I can never remember that website. The only thing I know is SDBS is basically Spectral Database System, and then the JP probably stands for Japan at the very end. So if I click that link, this is the website that shows up, and this is a website that's provided to you in your Blackboard site. You can just click on it, it sends you directly here. At the front page, if you scroll down, at the very bottom it says, I agree to the disclaimer. Basically that you're not using this for publication purposes or reproducing it illegally that you're not supposed to do. It's just for random research. That's what it is. So let's say I want to take a look at the database for ethanol. So I'm going to type ethanol into the compound name. If I know the molecular formula, I can also put it here. If I know the SDBS number, which you probably don't unless you use it quite often, you can type that number in here. Or the CAS registry number. All compounds have a CAS number. That's important. And they have tied the CAS number to that particular compound. All right, so I'm just going to type in ethanol. I'm going to hit enter. And then a whole list of different compounds show up. The reason that it gives me a whole list is because it might not have found ethanol, but look, it found ethyl alcohol. And anything with ethyl or anything with alcohol in it, it will typically peg into the search just in case you spelt it wrong or in case you meant one of those. But here is the ethyl alcohol. That's how I should have typed it. That's how it's entered into their system. And then I see all of the Y's all the way across. Y, 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 Y. Y means yes, N means no. Go figure. All right, so basically what this means is that, yes, it has a mass spectra into the system. Yes, it has a carbon NMR. Yes, it has a hydrogen NMR. And yes, it has a infrared spectrum. And that's what I want because that's what we're talking about now. We'll look at these other things when we get to them, but we're only focused with infrared. If I come down and click the Y under ethyl alcohol, then the infrared of that compound will show up. And if I ran ethyl alcohol in my laboratory and I didn't have a database on my software, but I wanted to compare it to something to see if it makes sense, this is what I would compare it to. So it gives me a nice dip with the OH group. It shows me the rest of the infrared spectra. Down here at the bottom, it's running from 4,000 to 500 in this case. So they extended on a little bit more. They tell you how they ran it up here at the top. So it looks like it's the liquid film, which is kind of normal. That's what you would want to run it as. And the units on the x-axis are matching what we always use. The units on the y-axis is what we always use, percent transmittance, and it shouldn't go above a 100, right? It might go a little bit above, but it shouldn't be at 120 or 140. If so, you're doing something wrong. But there's an infrared spectrum. I can do that with every single molecule that I want to search for in the database and quickly pop up an infrared spectrum of a compound. Over here to the left, it's going to break down a little bit more information, and you can scroll through and see the other things that they have listed for ethanol. And it looks like there's only one type of infrared that's listed, and that's in the liquid film category. So there's your SDBS, and you will be required to go in and search this database and find infrared spectra for various compounds. And this is the area that you would do that in. Okay? All right. So we are finished with the instrument as far as pieces and parts go. You now know how to run a sample. You now know why samples absorb infrared light. You now can interpret infrared spectra that's coming from the machine. And you now know pieces and parts of how everything works to give you that spectrum in the end. And now you even know that there's databases out there for you to cross-reference compounds to see what's present and how to identify these solutions that might be submitted to the laboratory.